Hello dear students, welcome to That's It YouTube channel. Today in 7th session we are going to discuss the concepts of organic chemistry. The classification of organic chemistry is not as simple as the physical or inorganic. As we know that the topics of general organic chemistry has connection with rest of the chapters, or the reactions of the hydrocarbons has some connection with the aldehyde or ketone, or the structure or the isomerism of the hydrocarbon is studied separately in GOC and isomerism. So it's very complex to classify the organic chemistry unit wise or chapter wise. However, I tried to classify that into various categories. Like you can see, the first session from organic chemistry is from general organic chemistry, isomerism and EAS, right? So let's quickly get into the question related to that. Let's see the first question, which has come from the practical organic chemistry. Just slightly I'll add POC also to this. Like various compounds are given over here, right? Aniline is mentioned. You know that aniline is nothing but aminobenzene. All right. Next you have cresol. Cresol means the substitution of CH3 and OH on the benzene. Cysteine is an amino acid which contains the sulfur. All right, isn't it? Caprolactam is 7-membered heterocyclic ring, which is actually responsible for the formation of what you call the nylon 6, many times asked in the JEE main exam also. Like you can see that how do you detect the extra elements in Lassine test, or how do you perform the test to identify the functional group which are present in the compound is actually the agenda. Like you can see, this compound has carbon and nitrogen. Alright, so this is having what? Phenolic group. So you need to identify what it has exactly. And this is having COOH, and this also having what? Sulfur and nitrogen as the extra element, and this group is also having nitrogen along with the carbon. So you can see that there is CN which is present in compound 1 and compound 4. Therefore, one option at least should match for compound 1 as well as 4, because the extra element is same. As we all know that when nitrogen is present along with the carbon, the sodium fusion extract contains the sodium cyanide, which is added FeSO4. As we all know, the reactions gives rise to what? Ferrocyanide. Alright, when this is treated with the excess of NaCN, gives rise to sodium ferrocyanide. Alright, now you may be thinking, from where do we get iron plus 3? Because iron plus 3 is only converting this into the Prussian blue, that is Fe4, FeCN taken 6, taken thrice, isn't it? So this is the formula of the Prussian blue complex. Alright, ferrocyanide, right? This is Prussian blue. Now this iron 2 is converted into iron 3 by the action of, you can see, concentrated sulfuric acid. So that is oxidizing the iron into iron 3, and some portion of the iron got converted into iron 3 as well, which is giving rise to the precipitate. Now we can see that clearly that aniline has a connect to option 1. And what is the second option? You can see sodium fusion extra gives rise to a blood trailer that is related to sulfur, that we will see later. Aniline addition of sodium bicarbonate is related to COOH, we will see later. The compound reacts with bromine water to give a white precipitate. Again, this is matching, you can see. Alright, we know this is very important reaction of phenol as well as aniline. So what's happening here, that aniline, when reacts with bromine water, orthopara substitution of the bromine takes place, that is electrophilic aromatic substitution. That's why I clubbed it with EAS over here, to give you tribromoaniline. If it is tribromophenol, that is white in color, whereas this is yellow in color. Sorry, that is yellow in color and this is white in color, right? So white color PPT. If it is phenol, you will get yellow PPT. If it is aniline, you will get white PPT. So this One is matching with P as well as S. You can see the only one option which is matching to it is nothing but D, but we will check the remaining also. Like you can see, this is having phenol, and you know phenol gives rise to the violet coloration when added to the FeCl3 because of the free radical formation. So this is upfront, right? You know, you can see that this is matching perfectly. 2 is matching to what? T, isn't it? That thing is done, so it is justified that 2 is matching with T. Third is matching with Q comma R. Let's see how. Third is matching with Q comma R. We got the answer first, right? But that's not the point. You can see here that this compound has what? Sulfur. So this sulfur gives rise to sodium sulfide, and this is when treated with Na2FeC and taken 5NO, that is sodium nitroprusside, gives rise to Na4 FeCN taken 5 NOS, which is actually the red color PPT, right? So because cysteine contains sulfur, the test related to that is nothing but Q. Alright. Addition of the compound to a saturated solution of NaHCO3 give the effervescence is also cysteine, because you know that cysteine has what? COOH. You know that COOH gives rise to the effervescence because of the evolution of carbon dioxide gas, isn't it? So third option is matching with Q comma R. Alright. Fourth option, you can see caprolactam again has cyanide. That means what? The caprolactam has a connection with P as well, right? So this is the matching can be done, right? So practical organic chemistry linked with various other topics, isn't it? So first question looks to be complex, but you can do it once if you identify the group that are present. You can see the second question is actually has various reactions like, you know, Clemmensen reduction, nucleophilic substitution of OH by Cl, electrophilic aromatic substitution, right, Friedel-Crafts acylation, and you have again Clemmensen reaction. So what happens here, you can see that the electrophilic aromatic substitution will take place once if AlCl3 attacks on this, it's going to give you the oxygen AlCl3 minus, and this bond will be broken towards the oxygen to create electrophile which is attacking on the benzene, right? So let's write that. So hydrogen is being replaced, so acylation is taking place. Alright, C double bond of CH2, CH2, C double bond of OH. The hydrogen is replacing AlCl3 minus. So this is your compound P. You can see when this compound P is treated with zinc amalgam and HCl. Beauty, isn't it? You know that it is going to reduce the aldehyde ketone but not carboxylic acids. So what you are going to get here, after the formation of P, you are going to get C double bond of OH. So this is your compound Q. Alright. Next is what? Q when treated with SOCl2. You know that OH will be replaced by the chlorine, isn't it? You know this reaction, right? OH will be replaced by the chlorine. So this is your compound R. Now this is when treated with AlCl3. Again the same thing, electrophilic aromatic substitution, that is chlorine goes and this hydrogen is replaced. That means the link is established over here, isn't it? So what do you get? CH2, C double bond. So this is nothing but your S. When it is heated with zinc amalgam and HCl again, the last compound obtained is just a hydrocarbon, isn't it? So this is your final compound. Okay, got it? So these are the structures that we have when you are doing this successive reaction. So compound P and Q are carboxylic acid. Let's check that, right? You can see you have P and Q. Both are having what? The COOH groups. That's true. Compound S decolorizes bromine water. You can see compound S, you know, it doesn't have any carbon-carbon unsaturation, so it is absolutely wrong to say that it decolorizes bromine water, isn't it? Compound P and S react with hydroxylamine to give the corresponding oxime. This is nothing but the property of aldehyde and ketone. So let's see P and S. You can see you have got what? P. Where is P? Yeah, P, you can see that it has a ketonic group. And where is S? Where is this? Yes, it too has the ketonic group, so this is also matching. Compound R reacts with dialkyl cadmium to give corresponding 3-degree alcohol. Where is R? You can see that this is the compound that we are talking about. Let me write it over here. Alright, acid halide. When react with dimethyl cadmium, CH3, taken twice, CD, what you are going to get? You are going to get C double bond to CH3. That means you will be getting what? The ketone. Alright. Okay. But when you treat this with excess of dimethyl cadmium, it's like a Grignard reagent. You know that you are going to get the 3-degree alcohol. Alright. So this is also correct. So in certain text I found that this is given as incorrect. That all depends upon the number of mole that we have taken. If you take limited amount, the reaction would stop over here, giving rise to what? Only the ketone. If it is taken in excess, obviously that gives rise to the 3-degree alcohol also, because nothing is mentioned whether you take 1 mole or 2 mole. This was kept like a suspicion, right? You know, no one said that it is the correct answer, or in some text it is given as wrong answer, right? As per the official key, it is given as the wrong option. That means that we have taken actually 1 mole of dimethyl cadmium only. So it is not very certain in certain questions of JEE, right, at times. So we have to speculate at times. Alright, so next let's see the other question. Very easy question. You can see there is a paragraph related to the reactions of what you call methane undergoing the chlorination, isn't it? Methane undergoing the chlorination, and accordingly these things are given, the information delta H and all those values are given, as you could see. Now this clearly says that if any free radical is formed, you know that these reactions are free radical substitution, right? So free radical substitution means it depends upon the stability of R radical, and as far as stability is concerned, you know, benzylic greater than allylic, 3 degree, 2 degree and 1 degree. This is how you interpret the stability, isn't it? So if any carbon hydrogen that is going to produce a stable free radical will be broken easily, so this bond energy will be low. I'm just writing this, taking this as a reference. Don't think that this is low. Taking this as a reference, as you could see that if this is producing a stable free radical, the energy which is required to break that bond will be lesser, because that is stable, right? So you can see among PQRS, the most stable is being benzylic. So this could be easily broken, right? So Q is matching with the least value. So Q is matching with what? Q is matching with 4. Alright. Q is matching with 4. Isn't it? So Q is matching with 4 is only in one option, that is in option A. So we got the answer anyway. So you can see P is giving rise to a 2 degree radical. This is vinylic and this is acetylenic. You know that they are what you call, not here, they are less stable, so they require more energy. So after this, I mean to say, the easily broken bond is what? The Q. The Q is equal to 4. You can see P is equal to 3. Next easily broken is this, right? R is 2. And it's very difficult to break this bond, because you know that this carbon is sp hybridized, more electronegative. More electronegative does not break the bond so easily. It has greed for the electron. It won't let that carbon hydrogen to lose its electron, isn't it? So right answer for this question is option A. Sometimes you can get the answer by looking at a matching with only one option, isn't it? Right? Easy question comparatively. There is another question related to this. You can see that there is a data which is given, and it is being given that there are various statements related to the overall reaction CH4Cl2 gives rise to CH3Cl and HCl. Various data is given, and based on that you are going to get you are going to find out the actual answer to the delta H naught, right? You can see the reaction is exothermic with delta H or endothermic with delta H or whatever, you know, you have to find out. Again, you have to go back to the actual reaction sequence to do that. All right, let's see this. You can see what's happening here, right? You know, you got CH4 breaking into CH3 dot H dot, then Cl breaking into Cl dot Cl dot. Then you can see you have to eliminate CH3 radical. For that, I have to write the opposite of this reaction, that is CH3 dot plus Cl dot giving rise to CH3Cl. Alright, I am going to eliminate the H radical also, so I am going to write the opposite of that reaction, and accordingly I write the heats, right? Now here is 105, it is 58. You can say I have written the opposite of this, so it will become minus 85, and this is also minus 103. Now when you are clubbing all these, you can see that your H radical got cancelled, isn't it? Two chlorine radicals gone, CH3 radical is gone. So what is the net reaction? Net reaction is what? CH3Cl plus HCl, and the total heat which is involved in this process is 105, 58, minus 85, minus 103. This is nothing but minus 25. You can see that the overall reaction is exothermic, isn't it, right? So what is the right answer for this question? Right answer for this question is exothermic with delta H naught is minus 25 kilocalories. Easy question. Now let's see another beautiful question from the isomerism, clubbing it with, as I said, the carbohydrate part. You can see the basic property of the glucose is the reaction with HNO3, very frequently asked, isn't it? So what is the product which is obtained in that reaction? You can see that COOH is obtained when the CHO and CH2OH are oxidized. So you need to write the product of this reaction first. Rest of the groups are unaffected, they remain intact. Alright, HOH. So this is the P which is having 52.7 degree optical rotation. But we are talking about the compound which are obtained among these options. We are given certain compounds. Now these compounds, when subjected to the oxidation, you are going to get a compound which is having exactly opposite to 52.7, that is minus 52.7. That means here they are talking about what? The enantiomer of this, right? What is the enantiomer of this? COOH, COOH, as you can see HOH, opposite non-superimposable mirror image, HOH, HOH. So they are talking about this product which is obtained by the oxidation of this, right? You know, you have to look this compound which is having minus 52.7 degree optical rotation. However, this compound has plus 52.7 degree, right? So you can see that when I am oxidizing this, I am outright writing the products of the oxidation. I am taking this as the COOH, right? This is undergoing oxidation. I am writing the oxidation product. I am converting them into the oxidation products. Look at it, right? You know, when you look at this, is it matching? No, you can see this part is missing, right? This is not matching. Over here, this is also not matching. In either perspective, you can see that this is not exactly matching. All right, is it matching? If you look at from the bottom also, you need to check. It's not that you are looking only from the top, you have to check from the bottom also, because the ends are same in both the cases, isn't it? So you can see 2 OH are on this side, right? Now when you flip it also, you're going to get the OH on the right side, right? Now when you are flipping this compound, so that the 180 degree flip, when we do that, the groups will get opposite. However, they are on the left side here, you might get it on the right side. Next option, you can see option C is perfect, because you can see it is nothing but this compound. What about the option D? When I am flipping this compound, I need to check. You see, when I am flipping it, you get COOH, COOH, isn't it? When I am flipping this, you know that the 2 HOH, right, doing the opposite of this, which are on the right side will go to the left, isn't it? And these two groups also will interchange their configuration. So option D also seems to be matching, isn't it? So right answer for this question is option C and D. Alright. Let's see another interesting question from the what you call conformational isomerism. Linking it with what? The beautiful optical isomerism. Here the compound which we have taken here is mesobutane 2,3 diol. Alright. So this is the compound that is being taken, meso. Alright. Various conformational isomers are given, and you have studied that when two OH are adjacent, they attract each other by virtue of the hydrogen bonding. So you see that hydrogen bonding thing is existing in option B, C and D, but not in option A. Alright, isn't it? Now when I take meso, alright, so this is meso, right? All groups are on the same side or all groups are on the opposite side, one on the same, right? Now you can see that this is also meso, makes sense. And this is the Gauss conformational isomer of the same, where adjacent groups are, that is dihedral angle here, dihedral angle is 60 degree. Alright, so this is also the meso compound. First of all, you need to identify what is meso. So this is the Gauss conformer of meso. However, this cannot be the meso isomer because two Mes are opposite and here two hydrogens are opposite. So they are not meso first of all, they are not meso. When they are not meso, there is no point of comparison, right? Among A and B, the Gauss is more stable because of what? The intramolecular hydrogen bonding. If there are any bromine kind of groups that are present, then A would have been the right option. So right answer for this question is option B. We ruled out C and D because they are not meso. Alright, let's move on to the next question quickly. It's about the basic strength of various amine, and we have seen in multiple cases that NO2, which is bulky when present adjacent to the dimethylamine due to steric repulsions. What do we say here? Due to steric repulsions, this N-Me2 group goes out of plane with benzene. So coplanarity is lost. So what is happening here? There is no coplanarity. When there is no coplanarity, there is no point that this lone pair will involve in any sort of delocalization. So when you take the various substances, that steric repulsion does not exist here because this group is bulky but this is small. So steric hindrance exists only here, steric repulsion exists only here, right? Because of which nitrogen lone pair are intact. So basic strength of 4 would be definitely greater. Then comes your 2, because 2 methyl groups are supporting to the nitrogen, so that the basic strength increases. Then that NO2 groups are anyways decreasing the basic strength, so this goes to the last. Basic strength is decreased by the strong electron withdrawing groups at ortho para, isn't it? So the order of basicity is 2 greater than 1. That is wrong, absolutely. The magnitude of pKb difference between 1 and 2 is more than between 3 and 4. This is again a wrong statement, right? There is very less difference between these two. I'll call this as Kb1, delta Kb1, and this is delta Kb2. As we know that delta Kb2 is far greater than delta Kb1 for the reason that this is very basic because of the steric repulsion. This lone pair is not at all involved in any sort of delocalization. However, in all the 3 cases, you can see that lone pair is involved in delocalization. There is no point of comparison between 4 with rest of the 3 compounds. So this gap would be definitely greater. So the magnitude of pKb difference between 1 and 2 is more than 3 and 4 is absolutely wrong. Actually 3 and 4 is greater than 1 and 2. The resonance effect is more in 3 than 4. Yes, because you can see resonance is happening here, the plus M effect is happening here, whereas here plus M effect is not happening because of the steric repulsions. The planarity is lost. So is more in 3 than 4, that's true. Steric effect makes compound 4 more basic than 3. Yes, this is also true. That's what we have studied, right? So option C and D are the correct answers, isn't it? Let's see the next one. This question is beauty. I mean, this question is all about what? Degree of unsaturation, right? So now let's write. this compound C6H5, that is benzene, alright. And there is a C6H5 here as well. I am writing the whole group so that we can count the degree of unsaturation. And what's happening here when you are hydrolyzing this, you can see this is an ester group, alright. This is an ester compound which is hydrolyzed. You know, ester upon hydrolysis gives rise to what? This is C6H5 and this is C6H5. When ester hydrolysis gives rise to what? COOH. And there is a benzene ring here as well. Now, when this is heated with concentrated sulfuric acid, you know, concentrated sulfuric acid is a very strong dehydrating agent and H2O is lost. When H2O is lost, you are going to get very interesting compound over here, that is C6H5, C6, isn't it? H5, there is a C double bond O, and there is electrophilic aromatic substitution which is taking place over here, alright. So, removal of H2O makes 1, 2, 3, 4, 5 membered ring, alright. I will use a different shade, 1, 2, 3, alright, 1, 2, 3, 4 and carbon, this one is 5th. So, you can see the link is established over here, right, isn't it? Am I right? That link is established, right, in each carbon. Now, you have to find out the double bond index. I am writing that link over here. I am elaborating the structures. So, you have to find the double bond index, right? You can see double bond index or degree of unsaturation. That means ring or the pi bonds or both. You know that benzene, right? It has what you call 3 pi bonds. So, each benzene has 3 pi bond plus 1 ring. That is, each benzene ring contributes to the degree of unsaturation by 4, right? So, you can see that benzenes 1, 2, alright, 3 and then, am I right? Total how many benzenes are there? 4, okay, 4 benzenes, isn't it? If I am making any mistake, please correct me, right? That means 16. There is adjacent 1 pi bond present and there is a ring, right? So, 16 plus 2, 18. So, if you have any suggestions to make, please post them in the comment box. That will be helpful in giving the better lectures, isn't it? Now, we can see the next question. With respect to the compounds 1 to 5, choose the correct statement. The acidity of compound 1 is due to the delocalization in the conjugate base. You know, this when hydrogen is lost, the negative charge is very much stable by the delocalization of the 3 benzene rings, isn't it? So, the delocalization is proper, alright. So, that is taking place, isn't it? So, delocalization is taking place, that's true. Conjugate base of 4 is aromatic, yes, because you see when you are removing the hydrogen atom, the conjugate base which is formed is cyclopentadienyl anion. It has 6 pi electrons and cyclic delocalization, therefore, this is aromatic, 4 and plus 2 pi electrons. Compound 2 becomes more acidic when it has an NO2 as substituent, yes, that's true. When NO2 is present, you know, it's a strong electron withdrawing group and acidic strength increases. That's true. This is also correct. The acidity of the compounds follows the order. 1 greater, that's absolutely false. You can see that 4 greater, because this is leading to the aromatic species, no? So, loss of this hydrogen is very easy. This is very important and frequently seen in JEE exam, right? So, 4 is greater than what next? 5, because it is estellenic sp carbon atom. There comes your 1, alright, then is 2 and then is 3. So, this is the correct acidic strength order. So, this is wrong. So, right answer is A, B and C, right? Alright, hope you are understanding, hope you are following. If you are liking the videos, please press the like button. That will encourage me to make the better videos. Share it with those who are also preparing for JEE Advanced, right? These are tricky, important questions which are explained as much as possible in a easy way, right? And subscribe to the YouTube channel for more and more important videos in the coming time. Also, I am posting some concepts, especially in Telugu, right? I am trying to explain each concept in 1 minute only. So watch those videos also. They are helpful in understanding the concept, especially those who have joined 11th this year and also pursuing 12th. I'm going to JE, give JE or NEET examination in the coming time, right? So hope you are liking the videos. That's it for today. Keep watching.